In this video, we're going to discuss what happens when you mix a weak acid with its weak conjugate base. So if we think for a minute, just what if we had pure weak acid? So let's look at ammonium. If I had 1 molar solution of ammonium, if I had 1 liter of it, I'd have 1 mole of my chemical at the start. There'd be none of my products yet. They'd start breaking apart. My ammonium would break apart into my products. I'd lose a little ammonium. I'd gain a little products. Eventually, I'll reach equilibrium, and I could plug them into the equilibrium expression, H plus on top, base on top, with my acid on the bottom, and we could solve out what X is. In this case, we can probably assume minus X is really small by comparison to the starting 1 molar concentration, and so no quadratic necessary. We could just calculate this out and find that 5.6 times 10 to the minus 10 will equal x squared. Multiply the 1 up. X must be 2.366 times 10 to the minus 5. Take the negative log of that. We'll find that our pH is 4.626. So a 1 molar pure weak acid solution of ammonium should have a pH of 4.6. If we were to do that with the base, have a 1 molar solution of just the base. Well, the base is going to act as the base. The only source of protons in an aqueous solution of pure ammonia is going to be water. And so we're going to make ammonium and hydroxide. We'll have our starting 1 mole per liter. We'll have none of our products. We'll lose a little bit of starting material. We'll make a little bit of products. And we'll find our equilibrium concentrations. Well, this is acting as a base, so we need a Kb. Remember that our Kb times the Ka for conjugate acid-base pair must equal Kw, which is 10 to the minus 14. So we can solve Kb. I can divide Ka off both sides. Our Kb ought to be 1.78 times 10 to the minus 5. Plug that in. Products on top, so our ammonium, our hydroxide, they're both X. We have 1 minus X for our starting material, our ammonia on the bottom. Well, 10 to the minus 5 is pretty small versus our starting concentration. So again, we can probably assume that minus X is too small to really change that 1.0. And so no quadratic needed. We can solve out the hydroxide concentration. 1.78 times 10 to the minus 5 must equal x squared. Again, multiply my 1 up, same value. Take the square root of both sides. X equals 0.0042. That is our concentration of hydroxide, which means our pOH is the negative log of that, which is 2.375, and 14 equals pOH plus pH. So my pH is 14 minus the pOH, so 14 minus 2.375, 11.625. We have just a 1 molar solution of the pure weak base. We'll get a pH of 11.65. What happens if we then combine these? Let's just pour both into 1 container. Well, it's going to be 2 liters in size, and we're going to have 0.5 molar ammonia and ammonium. We dump our 2 separate 1 liter containers together, we get a 2 liter mix, and that effect is it's half molar for each. So I have a solution that is 0.5 molar ammonium and 0.5 molar ammonia. Instead of just being 1, we have added both materials at the same time. This changes our equilibrium. We now have an outside source of the conjugate acid or base. So instead of starting at 0, this would have actually started at 0.5. Or over here, instead of starting at 0 for the ammonium, it would have started at 0.5. This is going to change how we have to calculate things. Well, we can set it up with both present. We can just pick any reaction as both. by convention, we do that with the acid. So we would start with ammonium, breaking apart into H plus and ammonia. Our initial values, however, we'll take 1 liter of that mixture, so 0.5 mole of ammonium. At the moment, no reaction has occurred. This is the instant of mixture before any chemical reaction can happen. So there's no H plus kicking around yet. These chemicals have yet to start trying to reach equilibrium. Well, our ammonia is also 0.5. There's going to be some change. Well, in this case, if we're looking, my acid can fall apart, but my base, there's no H plus yet. So the way we generally think about this is that, well, our acid still has to fall apart. We're going to make some H plus, and we're going to make some base. We're going to reach some equilibrium here. 0.5 minus X, X, and 0.5 plus X. It's still an equilibrium calculation, though. It's still Ka equals the products over the reactants. So 5.6 times 10 to the minus 10 is going to equal our H plus, our ammonia, all over our ammonium. So that's going to be X for the H plus. That's going to be 0.5 plus X for the ammonia. And it's going to be 0.5 minus X for the conjugate acid, for the ammonium. Now we can multiply this out and do the quadratic if we wanted. We'd multiply this part up. You'd end up with 2.8 times 10 to the minus 10 minus 5.6 times 10 to the minus 10x equals 0.5x plus x squared. You could rearrange. However, we'll save ourselves the trouble. Again, Ka is pretty small, so we probably can ignore the loss from our weak acid. It's rid of one of our parts. But what about the gain? Well, we're assuming X is going to be really small. In fact, it has to be extra small this time. If you think back to when we just had pure acid, we only ended up with 10 to the minus 5 of my ammonia before we reached equilibrium. If I have 10 times more of one reagent, I have to have 1/10 as much of the other. So if ammonia goes up by 10 times, then my H plus has to go down by 10 times. And if I go up 100 times, it has to go down by 100. If I go up 1,000, it has to go down by 1,000 to make sure the equilibrium is balanced. So by having a significant amount of ammonia already present, orders of magnitude more than would come from just the weak acid breaking apart, my H plus has to go down a lot to make up for it. As a result, X is going to be very tiny, and we can ignore it from what it gained for ammonia as well. This simplifies our calculations enormously because now I just have, well, in this case, the same. So my ammonia and my ammonium cancel out. Usually they'd just be whatever their starting amounts were. So they cancel, and really X just equals the Ka. And so I can say that 5.6 times 10 to the minus 10 is equal to the H plus concentration. And take the negative log of that. And what we'll find is that the pH for this mixture is 9.25. Well, that's different than either of the pure solutions. We could have a 4.6, an 11.6, or if they're mixed half and half, a 9.25. When you combine the weak acid and weak base, you will get a different pH out as the two chemicals interact with one another. In this situation, we had equal amounts of the two, but as you change them, you change that equilibrium position. Instead of perfectly canceling, if you have a little bit more of one and a little bit less of the other, well, you'll have to multiply and divide those across, and that's going to change the value X is equal to. The net effect is the ratio of your weak acid and weak base are going to affect the pH. Mixtures of weak acid and weak bases actually allow us to tune the pH. Instead of just getting a set pH, because that's what that chemical will do when it's alone in solution, how much we mix of both the weak acid and weak base allows us to adjust that pH. And we'll see that in our later videos.